connect up. All right, this week main goal is kind of today and Wednesday, looking at homework 2, trying to wrap that up by Wednesday, and then Friday goal is finish up project 2 so that we can get into module 3 kind of halfway through the month. So like, yeah, by next week. I mean, it's okay, like we can push off project 2 if we want to spend Friday and Monday. Well, I guess Friday we were planning on not meeting, but if we want to take a day on Monday to answer questions, we could do that and then turn in on Tuesday. And then start up module 3 next week. That would work, like logistic wise. So let's update that. So we'll say project 2, we'll push this off till Tuesday, so we actually have time to think about it. And yeah, then we're good to go. Now we got homework 2 is kind of what we're finishing up today and Wednesday. So last time we kind of looked at, usually the things that come up are like trying to create this plot where you're looking at individual markers for each designer, like how to separate that. We went through that last time. At least my main like process for kind of doing this is like, if I can do it once, then I can do it as many times as I want, because the computer has no problem automating the same workflow that I can come up with. And then the other thing people usually have some trouble with is Monte Carlo work. Is anyone making progress or have questions on like doing Monte Carlo kind of stuff? Nothing you want to admit to the World Wide Web. All right, I'll check in, see what people are up to, and then come back and try, see what else we can work on. That one can either be just like a semester table lookups or a semester of derivations. Yeah. Yeah, most engineers don't care for the derivation. It's more like the final result. An error. All right, so here's a question. I have all the transistor, so over here is like transistor count. Down here is our date. Gordon Moore said every 2 years the number of transistors would double. And so I put all my data onto this XY, so assuming that transistors are time dependent, like number of transistors, plotting them, then I do a best fit of like on a log scale, and I get one number says 0.33, another number says negative 654. So the question is, was Gordon Moore correct? Like, was it right? Are the transistors doubling every 2 years? Or are they not doubling every 2 years? Like, just based on what I have here. Think about it. Like, how do we know? How do we know or not know? Or is it just like no way to tell? Yeah. That one, is it log 2? So this is 0.31 log 2? Yeah, so this one is telling us kind of like at year 0, how many transistors were there on a log scale. So intercept is not really what we're looking for. Yeah.
Well, just kind of like loosely looking at it, it looks like it, goes up power of 10 every 10 years.
Okay. Yeah.
So maybe you could interpolate that down to 2 years and say, okay, we're probably about doubling.
Okay. So you're thinking like from here.
So we go 10 to the 4th at 1980 and then 10 to the 6th at 1990.
Yeah.
That's 2 orders of magnitude.
10 to the 4, 10 to the 6. And that was maybe 14 years, is that right?
Looks like 14.
Maybe 14. But yeah, 10's a pretty good, we're on a log scale, right? Ten to the 2, right? So we went up by a factor of, so what is that one? Yeah, like 100. So 100. So is that every 2 years? Does that tell us every 2 years that it's doubling? Do we need like more information, or do we have everything we need? That's what I'm, like, we can always do more, explore data more, something. Thinking. I mean, if we take 100 divided by 7, 14, so it's 14 times as much? Does that sound right? Seems weird, right? A factor of 100 every 14 years. What does doubling every 2 years look, what would that even look like on a log plot? Is it a straight line? It doubles every 2 years? Let's find out. Let's say x0 is 1. How long do we have? 40? All right, so if I just take the number 1 and double it, it becomes 4, and then it's 8, and then 16, like just 2, 2, 2 every, and it just kind of looks like this, where it just gets really, it looks really small for a long time and then gets huge. So some kind of exponential, basically exponential growth. It's just, so now I'll put it on a log y, so I'll change the y-axis to log. Is this growth like that? What is it going to look like? Is it going to be a curve, a straight line, a flat line, negative line? If it's doubling, this one's doubling like every 0, 1, 2, 3. It just doubles every time. So if I put it on a log plot, what is it going to look like? A line? Yeah, it should be some kind of straight line. So just straight line like that. So when we take the log of that information, create a straight line, like do a line fit, and then put it back on there, really we're finding the slope of this kind of straight line. Like, okay, there's some kind of exponential growth, and we're looking for what is that exponent of growth. What is this slope that's doubling every year? Is it a slope of 2? What do we think? Is that also 10 to the 4, something like that? 10 years, 10 to the 4. Not quite, right? Thinking about it. All right, I'll let it. Yeah, what does this mean? We did a thing. We plotted some stuff. We did a fit. What does that fit actually tell us? What do we know about it? Well, if it's a straight line on a long line, there's got to be some kind of pattern. I mean, the red line, like we assumed it was the that is the best fit linear. And it seems to, there's some data outside of it that can seem to go with I don't know, it's like looks right to me. Looks right, yeah, it's a log scale. Yeah, so I guess that's the question. It's like we did a fit. We Yeah. Oh, okay. Yeah, that one is just like in a folder on. Yeah, that, I mean, that's like the easy way, but you can download like everything from, you know, then you have your own. Yeah. Yeah. Okay. Yeah. So now, you know, okay. I mean, yeah, you can do either one. Because everything's listed on the download. Yeah, because the transport that was really just, yeah, I wanted to make a quick click a button so they're in and stuff. It's a good start. Yeah. Okay. Yeah. Around two, right? Okay. Yeah. All right. All right, so we had some, went around, talked a little bit about like, what does this mean? Like, do we have a fit? And I didn't hear any naysayers saying like, no, 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 there's some kind of higher order function here. Like, we definitely have noise in the data. It's not an exact straight line. There's stuff, other stuff happening, but it feels like this line is going through our data. So that means that it's a good fit for our, and we could like quantify how good of a fit it was, like how much we reduced the standard deviation or anything. But when we're looking at, like when we have data like this of like, hey, I've got an intercept, I've got a function, really what we did was say like, there's some function of time that is e to the a t plus b, or like e to the a t times e to the b. So like that e to the b term is sort of our, that's our initial condition. So e to the negative 600 is like basically zero. There were 0 transistors on our like processors in AD0, and yeah, that sounds about right. It's also kind of nonsensical because we didn't start making them till the 70s, but whatever. Maybe there was someone out there with like a single transistor rock of like keeping track of 1 bit. Then really what we're saying here is like our function is an e to the at. So it's, when we're saying like, oh, it doubled or it tripled or 5x, it's like that e to the a term. Like, what is that e to the a? And then so in this case, like if I wanted to know how much it changed, I could say like, all right, my transistor from 2 years ago, I needed to multiply that by e to the 1/3 times 2. So 2 years later. And let's do it over in Python. Oh, 3.35. Get a couple of sig figs in there. So 1.9577. That's how much, like each year, we had 195% or 196% growth. Is that close enough to 2? Or should we say no? Gordon Moore was absolutely wrong. It was not doubling every 2 years. From our estimates, it's only 196%. It doesn't count. It's not close enough. I guess it depends on how far along you are in your engineering intuition. Some people are like, sig figs matter. We're also on a log scale, so you can see like roughly how sensitive it is, like 3.4 versus 3.35. It's like 2 versus 1.95. Get a sense of like how close we can actually get to it. But so I bring this up because part of this module, and especially like in the project, goal is like, yeah, you can do whatever you want to data, but data does not speak for itself. Like, people will use that term of like the data speaks for itself. That is not true. The data you choose and how you process it and how you display it, that's what speaks, not the data. So you're the one telling the story. So in this case, if you wanted to make the story that Gordon Moore was off his rocker, there was no way he didn't predict it, there's too much other stuff going on, you can make that story because you could say, look at all this data that doesn't follow the doubling every year. And you could say, all of this was not doubling, or you could look at individual stuff. Or you could average it and say, it's basically true, like, get off, like, it's fine. But that's up to you, how you want to actually display the work that you're doing. So there's also like log2. Like you can take log base any number, right? So if I take the log base 2 of all the transistor counts and then do a fit, then my coefficients are 0.485 and negative 9.45. Still the same slope, because all I'm doing is like putting it into a log scale and then taking it out and then putting it back in. Nice part about this one is that if this number was exactly 0.5, then it would say that it's doubling every 2 years, because it's 50% bigger every year. So it's 100% bigger every year, or every 2 years. So now we have like a direct number, like this was 48% instead of 50%. All right. Anything else coming up for homework 2? Data processing, interpretation, analysis? Yeah. Yeah. Like looking at buckling of structures. Yeah. Yeah, and so here when we're looking at like so what we're doing here is like propagating uncertainty, which is like I know the things that I'm building with, I know the dimensions will not be perfect because it's just, they can't be. They all have to have, in this case, the main thing that we're looking at is the radius of our steel rods. So because that's changing, and because radius is part of our buckling load, then the more the radius changes, the more the buckling load is changing. So it's not, usually Monte Carlo simulations are we're using random numbers, but it's a very specific equation. Like the equation is propagating those random numbers into new forms. So one way that we can think about this is like, okay, radius is a normal distribution. I'm going to assume the buckling load is also normal distribution. So let me figure out how change L until I know a normal distribution is only 2.5% less than the applied load, where the applied load is going to be 1,000 kilograms divided by 100 rods. So it's 10 kilograms per rod, or 98 newtons, I think about 100 newtons. Because we're taking a normal distribution and squaring it twice, it's not normal anymore, so buckling load is not normal. If you assume it's normal, then it's you're being a little safer, like there's a factor of safety built in, so it's not the end of the world. All right, but let's take a look at what's happening here. All right, so I have everything kind of built in. And for the most part, this is the Monte Carlo simulation. Make random radii, calculate buckling loads. That's it. That is a Monte Carlo simulation. You're done. You're an expert. Then post-processing, usually the next step is like, now you have a ton of data, so what do you want to do with it? In this case, I'm going to take the mean, standard deviation, but I also want to look at like what does the histogram look like? Or I could look at box plots, like I could process it however I want. So that's the steps that I'm taking here. So here, this is the actual Monte Carlo. Down here, this is all like post-processing. What do I want to do with that information? So I'll run that, and then I'm going to look at, again, bigger is better, smaller, more time steps is better, Monte Carlo, more radii is a better statistical kind of thing. And now let's just want to wait, RNG is not defined. All right, let me define it. Oh yeah, let me put L as 5 because that's the default, right? So with a length of 5 meters, 5-meter tall kind of structure, it's only supported by 100 rods, but this is telling me, like, if I built this structure thousands of times, how many times would I have these rods? If one of them buckles, then it's not good. The rest of them will start to buckle. Like they fail, they start failing. What is this thing telling me? Like this histogram, does it tell me anything? This is like buckling, the number of buckling loads, like how many times there was a buckling load versus at what load it actually buckled. What's the most likely force that it would buckle? Like where is that on the plot? Is it over on the far left? Sorry, far left? Is it over on the far right? Somewhere in the middle? What's the most likely thing that if I apply that load, most of the time the rods will fail? Right at the peak, so right here. So this is kind of like, if I'm designing for that, then half the time it's gonna fail because most of the time the rods are there. So I do not want to design for that value. So if this was 100 newtons, that would be bad because half of them are going to fail, half of them are not going to fail. So really 100 is somewhere over here. And I can figure out like how many rods failed because I have this PCR. It's full of different values, like these are actual buckling loads based on the radii. I could say like, well, how many are less than 98.1? A whole bunch of falses. I get 13,751. Sounds like a lot, but we got to divide by this n. And then let's multiply by 100 so we can look at percent. So that was 13.8% failed. That's too many because I only want 2.5%. So if that's too many, buckling, main way to make it not buckle is make it shorter. So I could try like 3 newtons. Now I can see my peak is moving to the left. Like it's not up there at 200 anymore. Well, I forget what it was before, but I'm pretty sure it got smaller. And now at 3 meters, I see only like 1% failed, like less than 1%. So 3 meters is it's like over designed. It's too short. I can make it taller. So that's kind of, and the main thing that people kind of miss in this one is that you have to compare, somehow you need some comparison between the buckling loads you're calculating, like that mean and standard deviation, or even the actual histogram, and the applied load. So that's, like, you can do all sorts of fancy statistics on that critical buckling load stuff, but you need some comparison to what are you physically loading the thing with, and that's the last step. Did that help? Okay, cool. All right, thanks a lot.